I am Carl Ross of the University of Portsmouth, the United Kingdom. The oceans. 3/4 of the Earth's surface is covered by water. The Earth's surface covered by water is over 10 times larger than the surface area of the Moon. The greatest depth of the ocean is found in Mariana Trench. This is 11.52 kilometers deep or 7.16 miles deep. Ocean resources. Methane deposits in the form of frozen hydrates have been found at depths of 2 miles and more, 4.83 kilometers or more. Off the coast of the USA, 30 gas fields have been found. In one gas field alone, it is believed that there is sufficient gas to satisfy the USA's needs for 105 years based on the 1996 consumption rate. Ocean resources. The quantity of this methane is about twice the amount of all fossil fuels in land and shallow waters. That is, this deep-sea methane, the mass of this deep-sea methane is twice the mass of all the oil, coal, and gas on land and shallow waters. If this methane is divided equally amongst all mankind, then each and every one of us will get a chunk of methane of mass of about 1,670 tons. Public transport versus private transport. Public transport is not much good in rural areas and suburban areas. It's good in cities. In rural areas, try taking 10 bags of garden refuse to the rubbish tip by public transport. Try taking your old and infirm relative to the hospital by public transport. Try doing your weekly shopping at the out-of-town shopping mall by public transport. Methane resources. The total value of this deep-sea methane is about 536 times the GDP of the USA. Some eminent people say we should leave the methane where it is. However, I believe that if the West plays on a level playing field and leaves the methane where it is, I doubt that the rest of the world will follow suit. The methane is too valuable to be left alone. Get used to it, we're going to burn it. Methane resources. This deep-sea frozen methane was discovered by Dickens and others. Dickens is from Rice University in Texas, the USA. The USA and Japan are vigorously searching the deep seas for this frozen methane, but not Europe. The map shows that the USA and Japan are searching for stores of the deep sea gas, but not Europe. Methane production. The deep sea methane has been produced by the action of archaea under high water pressures. Archaea are similar to, but not the same as bacteria. They are a group of prokaryotic single-cell microorganisms. Some of the methane is produced by the archaea through microbial metagenesis, while some of it is produced by thermogenic metagenesis, with the cracking of organic compounds. Here you see archaea halobacteria. It looks a bit like bacteria, but it's not bacteria. Cost of producing electricity per megawatt hour. Coal, 30 pounds, about 30 pounds per megawatt hour. Gas, 38 pounds. Nuclear power, 39 pounds per megawatt hour. Not that expensive compared to gas. Wind, 85 pounds per megawatt hour. Now here we have water, ice and methane hydrate joined together. This is used to compare the strength. Now here you see burning methane hydrate. Clathrate is a structure, and here you have burning methane hydrate, which looks a bit like water ice, but it's very different. And here you have a pressure-temperature relationship for a methane hydrate. The vertical axis is pressure and underwater methane deposits. Many eminent scientists believe that the temperature of the oceans has increased by about 0.5 to 1 degree Celsius in 1960. If global warming continues, the seas will continue to warm up, and this may cause the plankton to die, with disastrous consequences for marine life. If the temperature of the seas gets sufficiently high, the frozen methane can evaporate and catch alight. Bermuda Triangle. Many eminent scientists believe that the unexplained loss of ships and aircraft in the Bermuda Triangle were caused by the escape of methane gas. If, in the case of ships, if they become entrained in a large bubble of methane gas, they can completely lose their buoyancy and sink to the ocean's bottom without warning. Similarly, if a low-flying aircraft becomes entrained in a bubble of methane gas, it can explode without warning. Underwater methane deposits. Thus, it will be necessary to use the underwater methane to prevent it from catching alight. The methane can be collected by drilling a hole into the reservoir containing methane gas and sucking the gas out from under the methane hydrate. This will cause the pressure to fall in the area where it is frozen, and cause the methane to vaporize from the compartment into the reservoir immediately below. Retrieving the methane gas. It must be remembered that freezing and boiling points of liquids are not only dependent on temperature, but also on the pressure that the liquid is subjected to. If the pressure of the fluid goes up, the boiling and freezing points also go up, vice versa if the pressure goes down. This is why we cannot get a good cup of tea at the top of Mount Everest, because the atmospheric pressure at the top of Mount Everest is only about 0.34 bar, or a third of atmospheric pressure, and because of this, the water boils at 72 degrees C, and in the form of water, it cannot reach 100 degrees C. There we have a section of the Blake Ridge methane collection. Now here you have a drawing of the Earth's atmosphere. The Earth's atmosphere. About 90% of the mass of the atmosphere is contained in the troposphere, which is warming up and where the weather occurs. Less than 9% of the mass of the atmosphere occurs in the stratosphere, where aircraft fly. The ozone layer lies here. This absorbs the harmful rays of the sun. CFC gases damage the ozone layer. The Earth's atmosphere. About 21% of the Earth's atmosphere is oxygen, but 78% is nitrogen, and 0.3% is argon. These are not greenhouse gases. In fact, greenhouse gases are much less than 1% of the total atmosphere of the Earth. Water vapor is a greenhouse gas. It is the third most abundant gas in the atmosphere, but its lifespan is only a few days, and because of this, climatologists aren't too worried about water vapor. Carbon dioxide is the worst offender of the greenhouse gases. Its concentration is 0.038%. It is the fifth most abundant gas. Over the last 300 years, its percentage has increased by 35%. The problem with carbon dioxide is its lifespan is enormous, over 100 years. The greenhouse gases are carbon dioxide, methane, nitrous oxide, ozone, and water vapor. The present level of greenhouse gases allow the Earth to be inhabited by man. Without them, the Earth's average temperature would be about minus 90 degrees C. That is, we won't be able to live without any greenhouse gases at all. So we need some greenhouse gases, but not too much. The current average temperature is about 50 degrees C with the greenhouse gases. Now this is a carbon dioxide experiment by Dr.
And this is what Keeling produced. His measurements started in 1958 at 315 parts per million carbon dioxide in the atmosphere. And the first thing that you notice is a rise and fall each year, which is the seasonal variation in carbon dioxide. Even in these early years, you could spot a rising trend, but you only get a true picture of the power of this graph when you stand back and track the changes through the decades, such that here, today, 2008, we're at 386 parts per million. This relentless year-on-year rise in carbon dioxide is the one undisputed piece of evidence in the whole global warming debate.
It meant that nobody could seriously argue with one simple statement. The human race has steadily increased the amount of carbon dioxide in the air. The significance of Keeling's discovery is simple, because carbon dioxide is a remarkable gas.
I can show you how carbon dioxide affects Earth's climate using this heat-sensitive or infrared camera, which is purring away here, and a candle, this glass tube, which is hooked up to this rather large canister of carbon dioxide gas. Now, if I light the candle, you'll see that on the monitor, the camera picks up the flame perfectly. Look at that. The hottest parts are glowing white. Now watch what happens when I turn on the carbon dioxide.
Just keep your eye on the flame.
The gas is invisible, so you don't see it fill in the tube. But as it comes in, you should see the candle start to disappear. There it goes. Look at that. What's happening is that the carbon dioxide in the tube is effectively trapping the heat.
The candle's warmth no longer reaches the camera. Instead, it's absorbed by the carbon dioxide inside the tube. That's exactly how carbon dioxide works in the atmosphere. It traps heat, preventing it from escaping into space, and warms the atmosphere in the process. The more carbon dioxide there
The atmosphere. Do not worry, there is enough oxygen in the atmosphere to burn this deep sea methane, the mass of oxygen being about 100 times the mass of the deep sea methane. The mean mass of the atmosphere is about 5.148 times 10 to the 15 tons. The Earth's mass of carbon dioxide was 1.956 times 10 to the 12 tons. If we burn this methane, we will release about 2.76 times 10 to the 13 tons of carbon dioxide into the atmosphere. So we might as well get used to it and do something about it. Carbon dioxide footprints per person per year. These are approximate values. About 20 tons per person per annum in the USA, 18 tons per person per annum in Australia, 11 tons per person per annum in the UK, 6 tons per person per annum in Switzerland and Sweden, 3 tons per person per annum in China, 1 to 2 tons per person per annum in India, 0.1 tons per person per annum in Ethiopia, and only 0.01 tons per person per annum in the Chad. Carbon dioxide footprints. Thus, it can be seen from the previous slide that for Africa to get into the 21st century, it will need to burn fossil fuels. If mankind burns 2 tons of methane per person per annum and also uses the alternative forms of energy, then mankind should have enough fossil fuels to last us for about 1,000 years. Additionally, as a source of energy, fossil fuels are relatively cheap. The emerging countries' entry into the 21st century. Sir Winston Churchill once famously said, "Do not pull the tail of the Chinese dragon or you'll awaken it." The Chinese dragon is awake and flapping its wings. Soon it'll be in full flight. When this happens, 1 billion or so Chinese people will want private motorized transport. China is building 1 coal-fired power station every 4 days. The Indian tiger will follow suit. For Africa to join the Buff Club, they will need to burn more fossil fuels. Energy used by India. Currently, India's middle class is 50 million strong, and India has about 61 million cars on the road. Economists believe that by the year 2030, India's middle class will swell to 543 million, and India will have 613 million cars on the road. Now here we have the Indian car that will change the world, the Tata Nano. The people's car can seat 4 to 5. Here's another picture of the Tata Nano. Looks quite an attractive car. The Indian car that will change the world, the Tata Nano. Its capacity is 623 cc's, 33 horsepower. Its maximum speed is 65 miles per hour with a town consumption of 50 miles per gallon. It is a 4 to 5 seater and it's a monocoque chassis which is made from recycled beer cans. It meets EU requirements. Its current retail price is £1,200. It is petrol driven, but there's a diesel version as well. And here we have the rival to it. The Chinese-German car costs about £400, about $600. It is made from carbon fiber, which is 10 times stronger than steel, and carbon fiber does not rust. This is designed by Volkswagen and built by China. It meets EU requirements. It can seat 2 people who sit in tandem, rather like traveling on a motorbike, where they sit. It can do 258 miles per gallon, and it could travel up to 74.6 miles per hour. Chemical breakdown of methane. Methane consists of 1 part carbon and 4 parts hydrogen. That is, methane is CH4. If scientists can break down methane to carbon and hydrogen, the hydrogen can be burned without causing a carbon footprint or by using a fuel cell. Using hydrogen to power automobiles, ships and aircraft can prevent the environmental problems mentioned in the previous slides. CO2 emissions. Combustion of the methane will release 27,600 billion tons of carbon dioxide. This figure is some 110,000 times greater than Britain's proposed maximum annual emissions. If this CO2 is released into the atmosphere, it will increase the CO2 in the atmosphere by about 1,511%. The scientists and the technologists will have to address this problem. Now, this is an idea I had. It might be an extreme idea, but it's a possibility that nearby cities can be linked by road tunnels or tubes, so that the CO2 can be trapped and scrubbed or injected into the ocean's bottoms. CO2 emissions. The Channel Tunnel, 32 miles long, cost $12 billion. It's very expensive because it was an incredible feat of engineering. A conventional motorway would cost about £28 million per mile. And my tube motorway, remember it's not a tunnel motorway, it's a tube motorway, it costs twice a conventional motorway, which is about £56 million per mile. Tunnels and tubes will have the advantage that they're weatherproof, so you're not worried about snow and frost and things like that. No gardening, no grit-laying will be required. Motorway noise will be less of a problem. If the tunnel goes past, if the tube motorway goes past a city, it will cause less of a problem. The green present land above the tunnel can be returned to nature. Similarly, the CO2 from factories. Now, this is an idea I had, a transport by road tube. It's a tube, it's above the ground, supported by foundations there. It's got 4 levels there. I've suggested 4 levels. It's just an idea. The bottom level will be emergency. The second level. So here's another view of the tube tunnel. The road tube is above the ground. If it goes through a mountain, then you'd have to have a tunnel. Now this is a conventional highway modified to become an enclosed double-decker. Double-deckers operate in the USA and also Mexico. The bottom deck is concrete. The second deck, I would suggest to be made out of composite, which has 50 times the strength of concrete in compression. In the case of a major motorway like the M25, which goes around London in England, it's sometimes called the biggest car park in the world because vehicles travel so slowly there. You can relieve that congestion by building another highway above the existing highway. This will prevent us from approaching our green and pleasant land. CO2 emissions. The longest tunnel is the Japanese Seikan Railway Tunnel. It is 53.85 kilometers or 33.5 miles long. The longest road tunnel is the Norwegian Lærdal Tunnel. It is 24.5 kilometers or 15.2 miles long. The above tunnels have water and mountains respectively above them. But my tube motorway has only air above it. Carbon removal. One method of removing the carbon dioxide is through the use of suitable chemicals. For example, if carbon dioxide is mixed with soda lime, it changes it into 2 harmless substances, namely chalk and water. Other chemicals that can neutralize carbon dioxide are potassium superoxide and lithium hydroxide. The above chemicals are already used in submarines and manned spaceships. Carbon removal. A German scientist called Klaus Lackner has invented a plastic which absorbs carbon dioxide. The absorbed carbon dioxide can be washed off the plastic by blowing it with water vapor. So if you apply water vapor to the plastic, you could collect the carbon dioxide and then reuse the plastic again. Other chemicals yet to be invented can be used for the same. Carbon removal. These chemicals can be placed in the exhaust of automobiles where they can be replaced at suitable intervals. The chemicals can also be placed inside tube and tunnel highways and factory chimneys where they can absorb the unwanted carbon dioxide. The unwanted carbon dioxide can be buried in the deep oceans where it will freeze due to high water pressures. Now, I'm in favour of burying carbon dioxide in the oceans because CO2 capture. The oceans naturally absorb about 50% of the carbon dioxide from the Earth's atmosphere. This causes the oceans to become more acidic as the carbon dioxide takes the form of carbonates, bicarbonates, and carbonic acid. If the oceans become too acidic, the plankton will die and cause havoc to marine life. However, it does have the advantage that the CO2 can be collected from the oceans and nullified. And this again is an idea I've had, don't know how practical it is, but nuclear powered ships can collect the CO2, freeze it and dump it overboard. This is a way that you could inject the carbon into the ocean's bottoms. This is a section of the Blake Ridge, which is off the east coast of America. The vertical axis, the depth, MBSF, that's the meters below sea flow. And I would suggest that if the carbon dioxide is pumped down there, due to high water pressure, it will freeze and remain there for millions of years.
And buried. This is a decade away. Critics say it's all far too slow.
Carbon dioxide hydrate formation at temperatures, pressures, and water depths. The left column, temperatures, the middle column, pressure, the right column, water depth. If you look at the bottom row, 5 degrees C, the water depth is 252 meters. So 5 degrees C, 252 meters, the carbon dioxide will form to hydrate, and deeper than that, it'll completely freeze. CO2 removal. Alternatively, frozen CO2 is called dry ice. Torpedoes can be dumped overboard a ship which is sailing over deep waters. As the density of frozen CO2 is 1.56 more than that of water, this frozen CO2 will sink. When the frozen CO2 reaches the appropriate depth, it will remain frozen for many centuries because of the high pressures. Some of the frozen CO2 will evaporate on the journey, but the bulk of it will remain frozen. Now this picture shows a ship throwing frozen CO2 overboard. It can be catapulted, but not fired, and it's a way of getting rid of the CO2. This is a picture of CO2 torpedoes sinking into the seabed. So the CO2, because the frozen CO2 is more dense than water, it's 1.56 the density of water. And this shows combating climate change. On the left you can see the ship which is throwing the CO2 overboard, and on the right you've got under the ship you've got a submarine tanker, and at the bottom right you've got an underwater drilling rig. The underwater drilling rig could either and here you see a pressure temperature equilibrium diagram for CO2. The vertical axis is pressure in atmospheres. The horizontal axis is temperature in degrees C, and on the left you can see where the CO2 is solid and gas. Up the top, CO2 is solid and liquid. In the middle, CO2 liquid and gas. Down the bottom, CO2 gas. Large structures that can dive to great depths. The average depth of the oceans is a little less than 3 miles, about 5,000 meters. For large structures to dive to these great depths, they will need to be constructed from composites or similar materials. The strength-to-weight ratio of a composite can be more than 10 times larger than that of ocean pressures. At the bottom of the Mariana Trench, the pressure is about 1,158 bar, or 60,800 psi, which is a little less than 8 tons per square inch. Now you've got to bear in mind that in London they have double-decker buses. Those buses weigh about 8 tons, so the pressure on a submarine pressure hull would be like putting one double-decker bus on each square inch of the pressure hull of the submarine. Enormous load. Currently, a large submarine can only dive to a depth of about 400 meters, or 1,210 feet. Large, deep diving submarines. If a submarine of internal diameter 10 meters, that's 32.81 feet, is constructed high tensile steel, and is required to dive to the bottom of Mariana Trench, then its design wall thickness will have to be a minimum of 2.3 meters, or 7.58 feet. which is enormous. If such a vessel is constructed of high-strength plastic composite, the design wall thickness will have to be a minimum of 0.91 meters or 2.98 feet. That is, it is buildable, unlike if it's made in metal and it's 2.3 meters or 7.58 feet thick. It has reserve buoyancy, unlike the high tensile submarine, and the high tensile submarine structure is so heavy that it will sink like a stone to the very bottom of the ocean.
Minus 530. 530. Minus 436.
29 if you can make it run. Don't get too close to it.
Brilliant! That was, look at that. I think that it just
This is the buckling or railcar tank under an internal vacuum. The railcar tank was filled with steam, and then it was sealed, and when the steam cooled, it turned into water, which has a much less volume than equivalent mass of steam, and it became under an internal vacuum and collapsed like that. And this is equivalent to a submarine or type structure under external pressure, but the pressure was less than an atmosphere, and it goes to show how one deep diving submarines. The only manned submarine to conquer the Mariana Trench was August Piccard's Trieste. This was achieved on 23rd January 1960. The Trieste had a spherical pressure hull of 6 foot internal diameter, which is 1.83 meters diameter, and it was about 6 inches thick. It was 15.24 centimeters. It was constructed in high tensile steel. It had no reserve buoyancy and helped it float. Its pressure hull was hung from a large 11 compartment float filled with petrol, which is called gas in the USA, as shown by the next slide. There you see the 11 compartment float above the spherical pressure hull. The compartments were such that they were filled with gasoline, or petrol as it's called in England, and the bottom of the gasoline tanks had holes in them so that the water pressure would compress the gasoline. It will not rise above the gasoline because the water is more dense than gasoline. And the gasoline tank would have internal pressure and external pressure would be the same, so it wasn't a problem. It's not going to collapse due to hydrostatic pressure. Unlike, there is a picture of the Trieste. You can see the 11. There's the Trieste at sea. And then the Trieste pressure hull with the plexiglass window. The plexiglass is called Perspex in Britain. Its scientific name is polymethyl methylacrylate. The pressure hull is about 7 foot external diameter, and you can see a man there who's about 6 foot tall. Give you the size of the pressure hull. And here you see Jack Piccard, who's at the back of the picture, and Lieutenant Donald Walsh of the US Navy inside the Trieste one prior to making that record-breaking dive. They're the only people who've conquered the Mariana Trench, and in fact, there's less people who conquer the Mariana Trench than astronauts set foot on the moon. Underwater drilling rig. The next slide shows an underwater drilling rig designed by myself together with my former student Jeff Lafley-Lane in 1997. The material construction of the rig was a high-strength plastic composite. The rig was designed to dive to a depth of about 5,000 meters, which is 3.11 miles, with a total mass of 40,000 tons. The rig had plenty of reserve buoyancy. A depth of 5,000 meters will be deeper than 60% of the ocean's bottoms. And there's the rig. Underwater drilling rig can pump CO2 in the water depths of 3,600 meters or 2.24 miles, where it will freeze and sink. It can also retrieve methane hydrates. If you think of the problem we had in the Gulf in 2010, Um, the conventional drilling rigs there were drilling. And there are the dimensions of the rig. The toroid, which is the donut shape, its outer diameter is 80 meters. Its internal diameter of the tube is 10 meters, and the whole thickness of the tube is 0.345 meters. This is the layout of the rig. You can see the drilling derrick in the top, in the vertical pressure vessel. It has a PWR nuclear reactor to drive it, which is housed in the living area, which is the toroid or donut shape. And this is Japanese drilling. The Times, April the 14th, 2008. About 3 years ago, hidden source of power could last 100 years. I think they've underestimated it. It lasts much longer than that. And Japan has found a way of retrieving the frozen methane hydrate. They pump water down a tube to the methane hydrate, melt and vaporize it, and take it up there. They reckon there'll be an action. Conclusions. For Africa to get into the 21st century, it will need to burn more fossil fuels. At present, fossil fuels are the cheapest form of energy. Public transport is not much good, except in cities. It's not much good in suburbia or in rural areas. The impact of the 1,200 Indian pound cars to be enormous, and so too is a 400 pound Chinese-German car. Other third world countries would like to produce similar cheap cars. This type of vehicle will probably be powered by deep sea methane, which is plentiful. Conclusions 2. It is likely that in the future many submarine pressure hulls will be constructed in man-made materials such as glass, boron and carbon fibers, and ceramic and metal matrix composites, and also carbon nanotubes. Carbon nanotubes are incredible material. It has 250 times the strength of high tensile steel and slightly more than a sixth of the density of high tensile steel. Submarines constructed in man-made fibers will lend themselves to be readily constructed in various forms. Retrieval of deep-sea methane together with the sea burial carbon dioxide can be achieved with the aid of deep diving submarine structures. Role of the scientist and technologist. The problem of environmental meltdown has to be addressed. According to Professor James Lovelock, within about a century, or maybe even longer, the temperature in the tropics will rise about 5 degrees C, and the temperate regions will rise by about 8 degrees C. This will cause our green and pleasant land to turn to desert. Role of the scientist and technologist. The effect of this will be to wipe out much of mankind, not in the present, in the far distant future. Lovelock believes that mankind will be survived by a few mating pairs inhabiting the Arctic and Antarctic circles in the far distant future. Immediate remedial action is required to alleviate the predicted catastrophe of biblical proportions. Positive feedback. James Lovelock says that 60% of the Arctic ice cap melted last summer. This will cause positive feedback and worsen the melting of the ice because planet Earth will absorb more sunlight due to the darkening of the Arctic Ocean. Because 71% of the Earth's surface is covered by oceans, and the oceans are getting darker, absorbing more sunlight, we have positive feedback. It's worsening the situation, and I reckon we can counteract this by placing mirrors on our roofs and elsewhere to cool Earth down by shining the sun's rays back into outer space. Additionally, we can paint our roofs and our roads with white paint to further cool planet Earth by allowing it to reflect more sunlight into outer space. White surfaces can also be floated in the oceans to reflect the sun's rays. We can cool the planet down. Role of the scientist and the technologist. Alternative means of producing energy must be used. If the scientists and technologists are given the tools, they can finish the job. We can save the planet, but we must not waste time. We can have our cake and eat it too. We can use fossil fuels and not destroy ourselves. References. This is the book I wrote in 2001, Pressure Vessels, External Pressure Technology, which shows you how to design a submarine pressure hull, published by Horwood, Chichester, but is now being republished, called External Pressure Technology, Pressure Vessels, External Pressure Technology, second edition, published by Woodhead Publishers of Cambridge. And this book should be ready at the end of April 2011. That is my homepage.